Want to do another one? You want to work on the rest yourself? Happy to do whatever.
Let's do C and F.
Okay.
C and F, okay. So, what is this?
Cyclopent.
Cyclopentyl. And we have an amine, right? And what's coming off of those amines? It's not hydrogen.
Methyls, yeah. So,
So
and
dimethylamine. Cyclopentyl dimethylamine. That's a tricky one because you could say, well, why is it dimethyl cyclopentamine? It could be. I would accept that too.
But if there was another substituent on the cyclopentyl group,
Yeah, we
then
have
it
to
would be a
put.
parent, and then
If there were another substituent on this group,
mhm.
it depends on the substituent, right?
Okay.
Like if this was an OH, then it would be NN dimethyl cyclopentanol.
Mhm.
And it'd be, right? So it would be three, I think that'd be 3 NN dimethyl cyclopentanol. Now, what if that was just a, like when you say a substituent, maybe here, like a methyl group, then that would be 3-methyl cyclopentyl dimethylamine.
Okay.
Or, yeah. Because dimethylamine, dimethyl amino, it'd have to be amino, and then it gets a little bit crazy if we put the amine in the front. But it could, right? If we look back on, whoops, some examples, right? We could put amino here, which would be then NN dimethyl amino 3-methyl cyclopentane. But we wouldn't need to do that because, no, strike that. If it were just a methyl group here, we wouldn't do the parent. We'd keep the amine as the parent. Okay. Does that answer your question, Lex, or did I misinterpret it? Like what?
No, that answers it.
Okay. All right. And you said F. Okay. So stereochemistry, and we have the battle of two substituents. Well, which one's going to get the name? The parent. The alcohol. So there are 6. So this is going to be cyclohexanol. Cyclohexanol. And then, right, we're going to name it number 1, 2, 3. So 3 amino. But now we need to put in the, I'll squeeze that over, but amino. Now we need to put in the stereochemistry, right? So what's 1s? Oh, I think I just,
Yeah.
Right, be S, because this is going into the board, right? So the hydrogen group's coming out. So how do we number that? If we just didn't worry about inverting it, what would we take preference?
The oxygen, hydroxyl.
Here. Yeah.
Head towards the amine.
And we say, well, that's R, but because the hydrogen's coming out, then we've got to flip it. Right? Okay. So that is 1s. And what about the amino group?
Also S.
Also S, because it's going to go this way. Right? Okay. So that's 1, 2, 3. We don't flip it though because it's coming out at us. 1s, 3s, dash 3 amino cyclohexyl. All right. Do A, B, and D, and then we'll go over those. You get it? All done? Alright, so first one. Nothing else to really compete, so 1, 2, 3, 4. 4 is bute, right? So butanamine. No stereo. Somehow you guys managed to pick the ones with no stereochemistry to work on by yourself. The easy ones. I think you guys have stereochemistry pretty down. So, and then what? 1, 2, 3. So 3 dimethyl butanamine. You get that?
Yep.
Okay. Cyclopentylamine. That was pretty straightforward. And what did you get for that one?
Triethylamine.
Yes. Triethylamine. In molecular research, there's a buffer called EDTA.
Oh, I've heard that.
Yeah, it's just to stabilize different components. Like for instance, if you're doing PCR and you need to run it in a buffer, and the TA part is triethylamine. So I think it's ethanolamine. Shoot, I'm forgetting the whole acronym, but triethylamine is a stabilizing compound.
Hmm.
Okay, so it prevents things from, it prevents enzymes from degrading to a certain extent, and it also prevents chelation of metals into like precipitates and stuff like that. All right, cool.
But what if the nitrogen is in the ring?
If the nitrogen is in the ring,
Mm-hmm.
yeah. So
Does that come later?
do we get to that? No. That's going to be those ones that we talked about here.
Okay.
So I'm not going to give you. I'm not going to give you things like that on an exam or anything, because we use all these different common names for them. How would we give it IUPAC? Let's see here. Give it systematic name. There we go. It's quinoline. So they don't even have IUPAC for those kinds of things. That is the system name. Okay. But I don't think it's worth your time memorizing all of these things. So. All right. So then, now, how do we make these? There are a couple different ways, and we're doing well. So, one is that we can make this nitrile intermediate, right? So we use sodium cyanide, we do an SN2 substitution reaction, we replace that bromide with a cyanide, then we use our reducing agent in excess and water to break that triple bond and protonate the carbon and nitrogen. Okay? So that's one very common way. And so essentially in the long run, right, what do we got? 5. So here we're taking off the bromine and we're putting on a full amine group. We're gonna put on an additional carbon and nitrogen, not just the nitrogen part. Okay. So if we had something here, this would be 1, 2, 3, 4, 5. That would be bromopentane. Right? Now we have 1, 2, 3, 4, 5, 6. We turn that into hexanamine, right? Okay. And these are things that we've seen before, right? The other major way is to use a carboxylic acid derivative and SOCl2, that's thionyl chloride. Okay, so sulfur thionyl chloride, and then excess ammonia. What that's going to do is that is going to replace the hydroxyl group with this. What is this? What functional group if we turn this into?
I don't know if the carbonyl enamine.
Amide.
Amide. Oh.
Right? So we take the carboxylic acid, we replace it with essentially an amide functional group, and then we reduce it. So we get rid of that carbonyl oxygen. So both of these are two-step processes to yield simple amines.
What does the SOCO2 do again? Does it make the OH group into a better leaving group?
Yeah, so it's gonna come onto here, and it's so at first we come in and bind onto here, and it becomes a good leaving group because oxygens aren't good leaving groups, right? But we can turn it into a good leaving group with the thionyl chloride. And then I believe the chlorine deprotonates the hydrogen, and we form hydrochloric acid. All right. So those are the two major ways, and we can go further if we're wanting to make aniline by using a nitric acid and sulfuric acid. You guys will remember that from when we were talking about substituting benzene rings, we can add a nitro group on here. And then you'll probably remember here, I think most often we use zinc chloride, but we can use other metals as well, and sodium hydroxide to reduce it from a nitro to an amine group. And this was the path we took. But we can also do a hydrogenation reaction, which I'm sure you guys remember this. So platinum, you take this is how we hydrogenate alkenes, right? To make alkanes, you put a bunch of platinum, you coat the bottom of your vessel with platinum, and they kind of serve as the arms that hand the hydrogens up to that double bond where the alkene is, right? Do the same thing here, essentially removing the oxygen and hydrogenating that nitrogen instead, and forming water. Okay. So two different pathways, but these are the three major tools that you can put in the toolbox for making amines. Okay? So, for this practice, what does this say? Draw the structure of an alkyl halide or carboxylic acid that might serve as a precursor to make these things. So, go back to those two, right, before this slide. Here's our halide. Here's our carboxylic acid, okay? If we want to make this, what halide? I would do both, right? Why not? What would be the halide? What would be the carboxylic acid to make this? Alright, so remember, if this is the final product, what we end up doing is we end up adding on that, right? So if we're going to start with a halide, it's going to just be
Purple.
that, right? We don't want to go out to that point. It's not just replacing a halogen with a nitrogen group. So, right? And then, if we want to do this, what's our first thing that we add to it? Our sodium cyanide, right? So then we get right? And then we add our lithium, aluminum hydride with water to get that. So then, same thing. If we wanted to do the carboxylic acid, right? No,
That one doesn't add any.
because we're not adding a carbon on there. Right? We're just replacing the oxygen, so it would be right? Does that look better?
I think one more carbon.
One more carbon. How many do we? 1, 2, 3, 4. Yeah. Okay. There.
Okay.
1, 2, 3, 4. Yeah.
Okay.
And then we add our thionyl chloride and go from there to just replace this with the amine group, making it an amide, right? And then we reduce that.
Yeah, reduce the carbonyl.
The carbonyl.
It goes away. Okay.
Yeah. All right, for this one, again, you're gonna have our benzene ring, and this carbon here, that's what we're adding if it's a halogen, so it's gonna be so just
Or would there be like one carbon in the middle, I think?
what's that?
I had it like one, the phenol ring, and then the benzene, then one carbon, then the halogen.
One carbon and then like this.
Yeah. Because we get 2 carbons overall.
We take this off. We want 1, 2. 1, 2. But if we do that, we take this off, then we add another carbon here.
Or no, the bottom carbon used to be a halogen.
Okay, so right, if we do, let's say we just use bromine,
Yeah.
like that.
Uh-huh.
Okay.
And then so the bromine gets replaced with the carbon and the nitrogen.
Yeah, there we go. Exactly, because then it would be carbon, nitrogen. Yeah.
Okay. Cool. Just making sure.
Yep.
That's
That's right. And then for carboxylic acid, what do we do there? We go 1, 2, so 2.
Mm-hmm. Yeah. So,
And then this last one,
bromocyclopentene
yeah.
or hexane.
Okay. And then we're going to do our carboxylic acid.
Azoic acid.
All right, cool. So pretty straight at this point. You've done so many different things that this is probably fairly straightforward, right? Okay. Guys, time, doing well on time. What's next? So, ammonia turns out is a very good nucleophile, all right? And so we can readily alkylate that when we treat it with an alkyl halide. So essentially, it's going to attack this iodomethane. Iodine comes off, and now we've made essentially a primary amine, okay? And then we can continue to do this to form now this product here. And it's going to get rid of that hydrogen because remember, we end up making ammonium in here. It's basic, it's going to accept the protons. It's hard to stop here though, okay? If you have excess halide, you're going to then make a secondary and finally a tertiary, and you can keep going into even a quaternary ammonium because it is such a good nucleophile. And so the quaternary ammonium would be if you had excess halide, and that is what you might have heard of quats. I don't know. Nikki, you'll hear about them eventually at school. But quats are short for quaternary ammonium salts, and those are antimicrobial in nature, so they're used.
They're used in restaurants too.
What's that?
They're used in restaurants too.
Oh yeah, to disinfect things. So if you wanted to get a primary amine, it would be hard. You'd have to do a 1-to-1 molar ratio of your ammonia to whatever halide you're using. And you're always going to make a mixed product. So ideally you would just settle for some cheap halide and somehow try to purify out or separate your mixed products to get the primary amine. You'll have some that are a primary amine, and then you'll have another product that's secondary. So it's really challenging. It is such a good nucleophile that it wants to just tack on those carbons all around.
So even if you start with a 1-to-1 ratio, like some of them will tack on more than one, or instead of all of them doing one first and then
Yeah,
okay, yeah.
exactly. You'll get a mixture of like secondary products, primary, and then some that didn't get anything, right? So you have 3 products, and I don't know what the abundance would be. I mean, maybe you'd have more primary than secondary and none, but no substituted. But you'd then have to find a way to separate that out. Okay, and this is kind of what that's talking about. So, right, we have a primary amine. If we have excess of that halide, we just keep tacking them on to eventually get, it's off the board here, but we eventually get our quat here. Okay, and there's not much coaxing that needs to be done. Just have an abundance of that, and it will readily form that quat. So it's a pretty cheap antimicrobial, which is probably why they use it in the restaurant industry, because it's economical, it's affordable, and you can use a ton of it to disinfect stuff.
Does it work kind of the same way by like interrupting the cell membranes, or?
Yeah, well, and also what it does is it will it's got this charge, and it will end up kicking off some of these methyl groups and then tacking on to whatever molecule is in that microbe and then altering that molecule. And then it can also intercalate into the membrane of like bacteria, and once it does that, it kind of pokes a hole in the membrane, which is not good for a cell to have a big gaping hole in it. I have a slide in my micro class that is much more fitting for an OChem class, and so I tell them, don't need to worry about any of this stuff. But maybe eventually I'll have a micro student take OChem. That's never, I don't think it ever really happens.
If I took micro after this class, I would have seen it a little different.
Yeah, most students that take micro go into nursing. And if you're going into nursing, you don't need a whole year of OChem. And no one would just, well, I won't say no one. Rare breed is going to take a year of OChem for no reason. So, all right, let's make it from nitriles and amides. What's this? That's a nitrile, right? What's this? That's an amide. So if we take our alkyl halide or our carboxylic acid and we put it in the presence of, again, nothing's changed here. We got our sodium cyanide and we've got our sodium cyanate and we've got our thionyl chloride. Using our excess, they've tacked on ether because that's the solvent that it's in, right? So essentially, right, lithium aluminum hydride and water, and we can make a primary amine that way. So here's some practice. Let's, I'll have you work on this between now and Thursday, and then we'll go over it first thing on Thursday, okay? Give you a little bit of practice with this. Propose structures for either a nitrile or an amide, or do both, right? If you can. Some of these, you may not necessarily, may not work, but what would we use as a precursor to make these amines? Right? So that's your homework for now. And then the last thing, similar kind of stuff here. We can take a nitrobenzene and we can put it, and essentially hydrogenate it, right? And turn it into an amine. Or we can take a nitrobenzene and this is typically in the past would be zinc chloride, but use some kind of metal halogen and reduce that down to. So this is reiterative, pretty much. We've done this kind of stuff. But okay, cool. Well, let's end early.